There's a construction in the book for how to build a Toffoli. H, control knot, T dagger, control knot, T, control knot, T dagger, control knot, T dagger, control knot, T dagger, control knot, T S. And I want another H after this. Well, another T and then another H. T, H. So this constructs a Toffoli gate. And it's not that hard to check. So in the 5 minutes, I'll explain, well, I will do at least one case for checking it. Let's assume this qubit is a 0. So to check it, all you have to do is make sure that it gives you the right answer when any of the 8 possible basis states is input. So let's take care of 4 of them by seeing what happens if this is a 0. If this is a 0, well, this does nothing. Oh no, if this is a 0, this does nothing. So this T dagger, T, cancel each other out. And now we have 2 control knots in each other. They cancel each other out too. And now we have another T and a T dagger, and they cancel each other out too. And now we have an H and an H, and H squared is 1, so those cancel each other out. Okay. So now we have a T dagger, control knot, T dagger, control knot, S. And if the first qubit, so this T dagger does nothing because it's T dagger applied to 0 does 0 because T was 1, 0, 0, I. So T dagger is equal to 1, 0, 0 minus I. So now this turns it into a 1. This T dagger applies a phase of minus I. This turns it back to a 0. This does nothing. So if this was a 1, this T dagger and this T cancel out. If the first qubit was a 0, then none of these do anything. So if this qubit is a 0, then this circuit does the right thing. You can similarly see that the circuit does the right thing if this is a 0. And if these are both her 1s, what you get is a T dagger followed by if first 2 qubits 1 get T dagger. Well, no, you get X T dagger, X T T, X T dagger, X T. T in with an H and an H on either side. H. T dagger is equal to 1, 0, 0 minus I, X T, well, okay, t equals 1, 0, 0, I, x t dagger x is equal to minus I, 0, 0, 1. So this is minus I, 0, 0, 1, 1, 0, 0, I, minus I, 0, 0, 1, 1, 0, 0, I, which is equal to minus, no, t isn't I, it's square root of I. I forgot, which is equal to, you have 2 square roots of minus i's and 2 square roots of i's, which is minus I, which is equal to I guess minus I times 1 minus 1. So this whole thing is a z. And there's a minus I on the front. And you get h, z, h, which is x. So this is x times a phase if the first 2 qubits are 1. And the phase is canceled out by this s. Or, well, it's canceled out by all these guys. So that is a sketch of why this thing is a Toffoli gate. So this proves that 2-qubit gates are universal for quantum computing. Okay. See, is there anything else? Are there any questions about anything? Yeah?
So any arbitrary unitary matrix can be decomposed using only 2 level gates.
Yes.
And when you do this, it always diagonalizes the identity. There aren't any zeros on the diagonal.
No, well, it always diagonalizes to, well, when you diagonalize a unitary matrix, you get e to the I phi, e to the I phi something along the diagonal. And then you have to fix those phases, but you can fix those phases with more, so I lied. So after you diagonalize it, you get e to the I phi 1, e to the I phi 2, so e to the I phi n. And then you need to do something to fix all these phases. But you can also do that with, 2-qubit gates, more 2-qubit gates. And in fact, I think you can actually do that with 2-level gates, but I can't be sure. Any other questions? Yes?
The first half of the circuit from target in C naught and the first is the third bit. These the first 2 bits don't change.
Yeah, it does.
So why do we need the second half of the circuit on the first bit?
Well,
Just want out that this bit.
well, so recall that if the first 2 qubits are 1, if the first 2 qubits are 1, so let's see, what happens when we cut the circuit?
If we remove the third qubit 11,
Yeah.
leave the Hadamard gate, but all of the gates after the line on the number 2.
Right. So what happens then is you get the circuit 1, 1, 1, 1, 1, 1, 1, 1, which is a Toffoli circuit, except actually this is a minus I, or something like that. You get the right circuit because it has a nasty phase you don't want in it.
But isn't the phase only of the
Yeah, so you want to remove the phase if both of these qubits are 1. No, because, you know, so what you want to do is you want to apply 1, 1, 1 I on first 2 qubits. So if you multiply 1, 1 on the first 2 qubits by an I, you cancel out this guy.
Why does the factor of I appear on the first two qubits?
Because you know, these qubits are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, or rather the basis states are this. And this is a bit where the first 2 qubits are 1. And you have, I believe, a minus I there when the first 2 qubits are 1. So if you could apply the circuit that multiplies by I when the first 2 qubits are 1, which is this guy on the first 2 qubits, 0, 0, 0, 1, 1, 0, 1, 1. Then this will cancel out this. So up to here, well, actually we need to put this H on the left here. So up to there gives you this circuit, or this gate, which is exactly what we want, except it has a minus I here. This minus I happens whenever both the first 2 qubits are 1. So we can cancel it by applying an I when the first 2 qubits are 1. And this gate we can do just on the circuits of the first 2 qubits. So this is another example of back action in that you would think that this doesn't do anything to the first 2 qubits, but it actually changes the phase of them under certain circumstances. It doesn't change, doesn't change 0, 0, 0, 1, 1, 0, or 1, 1 values, because in the classical, if you look at the classical basis values, none of these operations change it, but it does change the phases. And we need to undo all those phase changes.